Okay, in this section we're going to talk about applications of integrals to work problems. And so what we're going to do is, first of all, look here at the work done by a constant force. And here it says when a body moves along a straight line a distance d as a result of being acted on by a force of constant magnitude F in the direction of motion, we define the work W done by the force on the body with this formula. The formula is work equals force times distance. And so from this equation we see that the unit of work is the unit of force multiplied by the unit of distance. And in the international system, the unit is a Newton, where the unit of distance is a meter, and the unit of work therefore is a Newton meter. This combination appears so often it has a special name called the joule, and in the British system the unit of work is the foot-pound, and that's frequently used by engineers. So a simple observation: if you jack up the side of a 2,000-pound car 1.25 feet to change a tire, and we're going to assume you apply a constant vertical force of about 1,000 pounds, then you will perform 1,000 times 1.25. So that would be 1,000 pounds and 1.25 feet. So that would give you 1,250 foot-pounds of work on the car. Now, in the international system, you actually have applied a force of 4,448 newtons through a distance of 0.381 meters. So therefore, if you multiply the 4448 times the 0.381, you get 1,695 newton meters, which we call joules of work. So if we want to talk about the work done by a variable force along a particular line, we can do this. If the force you apply varies along the way, as it will if you are compressing a spring, then the formula W equals FD has to be replaced by an integral formula that takes that variation of the force into account. So the work done by a variable force, f of x, directed along the x-axis from x equal a to x equal b, is actually given by the integral from a to b of f of x dx. And the units of the integral are joules if F is in newtons and X is in meters, or foot-pounds if F is in pounds and X is in feet. So an observation: the work done by a variable force, say 1 over X newtons, from X equal 2 meters to 7 meters, you would simply integrate from 2 to 7 the function 1 over X, and you'd get the natural log of X. And we don't need the absolute value because these are going to be positive log or positive arguments. So it would be natural log of 7 minus natural log of 2. So that would be 1.25 joules. Now, one application of this work formula is Hooke's law for springs. Hooke's law states that the force it takes to stretch or compress a spring x units from its natural length is proportional to x. So in other words, the force is equal to some constant times x. The constant k, measured in force units per unit length, is just a characteristic of the particular spring, and that's called the force constant or spring constant. Hooke's law gives good results as long as the force doesn't distort the metal in the spring. Okay, so here's an example. Find the work required to compress a spring from its natural length of 1 foot to a length of 0.8 feet if the force constant is 20 pounds per foot. Okay, so consider the spring at rest laid along the x-axis from x equals 0 to x equal 1 feet. So here's the spring, here's 0, and here's 1 feet. Okay, so capital F of x equals 20x. That's the force required to compress the spring from 0 to x feet. So that's basically the kx that we talked about here, where k is 20 and x is the distance it's compressed. So to compress the spring from 0 to 0.2 feet, now that's how we get the spring to 0.8 feet. We actually have to compress it 0.2 feet. the force must increase from F of 0, which is 0 force, to F of 0.2, which is 4 pounds of force. Okay, so actually, if we want to find the work done, we just integrate from x equals 0 compression to x equal 0.2 feet compression of the kx, which is the 20x, and then we get 10x squared from 0 to 0.2. And so if we evaluate that from 0 to 0.2, we just get 10 times 0.04, which is 0.4 foot-pounds. So the work required there would be 0.4 foot-pounds. Okay, here's another example. A spring has a natural length of 1 meter. A force of 30 newtons stretches the spring to 1.6 meters. Okay, so it says find the force constant K. Well, we know that the force is equal to K times X, and since we know the force is given to be 30, and we know that it actually stretches the spring an additional 0.6 meters, then X would be 0.6, and then if we divide 30 by 0.6, then we can get the K value, which actually is 50. So now we have the K for this model here. So F of X, the force would equal Kx. So now it says how much work will it take to stretch the spring 2 meters beyond its natural length. So we're going 2 meters beyond its natural length. So we're actually going from 1 meter to 3 meters. So notice it says 2 meters beyond its natural length. So we are going to stretch it an additional 2 meters. So the integral would be from 0 to 2, this force function 50x dx. And then when you integrate that, you get 25x squared evaluated from 0 to 2. And that's just going to be 100 joules in this case. And then the last question is just really an algebra question. How far will a 45 Newton force stretch the string? So really, all you have to do is put 45 in here for the force and then solve for x. And so 45 equal 50x, so then divide by 50, and you get that x equals 0.9 meters. Okay, this gets a little bit more complicated here. A 10-pound bucket is lifted from the ground into the air by pulling in 20 feet of rope at a constant speed. Now the weight of the rope has to be considered here. The rope weighs 0.1 pound per foot. How much work was spent lifting the bucket and the rope? Now the work done by the bucket, that's actually constant because so all you have to do is multiply the weight of the bucket, which is 10 pounds, times the length that the bucket travels, which is 20. So that's actually just 200 foot-pounds. Okay, now the rope is a different story because the weight of the rope varies with the bucket's elevation. So it, that's going to be a variable function. Okay, so think of it this way. When the bucket is x feet off of the ground, the remaining portion of the rope still being lifted is going to weigh 0.1 per foot, right? 0.1 pound per foot times the number of feet. And so if the bucket is x feet off the ground, then you've got 20 minus x length of rope. So that actually is going to be our function that we integrate. So now we can find the work in lifting the rope by just integrating, because we know x is going to go from 0 to 20, 0 being that the bucket's on the ground and 20 being that the bucket's all the way up. And so we integrate from 0 to 20, 0.1 times 20 minus x, and then that's just going to be 0.1 times 20x minus x squared over 2, and you integrate that from 0 to 20, and you're going to get 0.1 times 400 minus 200, and that's going to be 20 foot-pounds. So the work required for moving the rope all the way up is 20 foot-pounds, and the work required for moving the bucket all the way up is 200 foot-pounds. So add them together and you get 220 foot-pounds. Okay, the next example is going to be pumping a liquid from a container. How much work does it take to pump all or part of a liquid from a container? To find out, imagine lifting the liquid out one thin horizontal slab at a time and applying the equation work equal force times distance to each slab. We then evaluate the integral that this leads to as the slabs become thinner and more numerous. The integral we get each time depends on the weight of the liquid and the dimensions of the container, but the way we find the integral is always the same. So let's look at this example here. We have a conical tank is filled within 2 feet of the top with oil that weighs 60 pounds per cubic foot. How much work does it take to pump the oil from the rim of the tank? So imagine the oil divided into thin slabs by planes perpendicular to the y-axis. So this would be like a thin slab of oil right here. Okay, now to pump it all out, we're going to actually go from 0 to 8 here. So that's how far we're going to move this oil. Now a typical slab here, since this is a circular region, it would be pi r squared times the height of the slab, which we'll call delta y. So since the radius of the slab is represented by y over 2, see the x value would be y over 2, from here to here would be y over 2. So the radius of the slab would be y over 2, so we square that and we get pi times y over 2 quantity squared times the height of the slab. Then the force required to lift the slab is actually equal to its weight. So the force in terms of y would be, remember the oil weighs 60 pounds per cubic feet, and now what's the volume of the oil? So the volume, I actually found the volume up here, which is pi times y squared over 4 times delta y. So multiply 60 times the volume, and if you multiply that out, you actually get 15 pi y squared delta y pounds. Okay. Now the distance through which this force must act to lift this rim is about 10 minus y feet. So the work done lifting the slab is actually given by 15 pi y squared times the distance, which is 10 minus y feet. So see, we have the force 15 pi y squared delta y, and then we multiply it by the distance it's going to be moved, which is 10 minus y feet. Okay. So finally, to evaluate this, we evaluate the integral as y goes from, let's see here, that should be y, but as y goes from 0 to 8, y squared 10 minus y dy, and that should equal 15 pi from 0 to 8, 10y squared minus y cubed dy again. And then when you evaluate this integral, and I'll let you do that, you should get 15 pi times 2048 over 3, which turns out to be 10,240 times pi, and then that's approximately equal to 32,170 foot-pounds for the final answer. Okay, I'm going to finish this section on another video where I'm going to do a special application, which is pumping water from what's called a glory hole. So I know you can't wait to see what that is.